Okay, so in this particular video, we have an introduction here to differentiate between average speed and an average velocity. So here's an example that I have for you. So here is a professional swimming pool. The length is 50 meters as shown in the diagram here. So we'll go from left to right of the screen. So keep that in mind as we take the direction of motion according to the diagram given. Okay. So it says during an Olympic 100-meter freestyle event, a swimmer completes the first 50 meters, so just the way there, in a time of 25 seconds, and it completes the entire race in a time of 48 seconds. So the distance there is 50 meters, and then the distance back is 50 meters since it is a round trip. 50 plus 50 would give you a distance of 100, which is what the event is. Okay, so there and back. All right, so here's how we do part A. Part A asks us to determine the swimmer's average speed for the first 50 meters. So apply what you already know from left to right, as the yellow arrow indicates there. The length of that pool is given in a diagram, which is 50 meters. So all we have to do is really apply the average speed function. The average speed function is simply the total distance traveled during that time interval. So therefore, we know the distance is 50 meters. And then the time given, because it says that completes the first 50 meters in a time of 25 seconds. So time would be 25 seconds. So if we simplify that, the average speed would simply come out to be 2 meters per second. So the swimmer averages at a rate of 2 meters per second on the way there. Okay. You notice here, part A asks for average speed, so I don't need to include the direction because speed is a scalar quantity. Okay. Part B asks you to calculate the swimmer's average velocity for the first 50 meters. So here I have on the screen average velocity by physics definition is the object's displacement, or the swimmer in this case displacement, which is delta x, and delta x is xf minus xi, your final position minus your initial position. Okay, but here without overcomplicating it, the swimmer starts from the left, swims a distance of 50 meters to the right, so therefore that would be moving in the positive direction. So here I have highlighted the positive sign there just to help you be careful in terms of getting your work done properly. So displacement is a vector, so it does have a magnitude, which in this case is 50 meters. It does have a direction, and the direction in this case, according to the diagram, it is to the right for the first 50, so we'll treat that as positive. So here we have 50 meters divided by 25 seconds, and your answer comes out to be positive 2 meters per second. The positive sign here indicates the direction that the swimmer is swimming in, because velocity is a vector. So unless otherwise stated with the word magnitude, if it asks for average velocity, you are expected to include the direction. Or you can say 2 meters per second, comma, east, or right, but you have to have a direction included if you ask for average velocity, because it is a vector. Part C asks you to calculate the swimmer's total average speed. Well, that's pretty light work. In order to calculate the total average speed, again, we just apply the average speed function one more time, but it says total, so the way there is also the same length. So here we have average speed is equal to distance over time, but the total distance in this case will be 100 meters because the swimmer ran there, which is 50, swam back, which is another distance of 50. So 50 plus 50 is 100, or the problem states so. Okay. Here, all we have to do is really do a little quick plug and chug. The total distance swam is 100 meters. The time given for the whole entire race is 48 seconds. So if you simplify that, you should get about 2.08 meters per second. No direction is needed because speed is a scalar quantity. So that's it. All right. Part C asks us to find the average velocity for the entire 100 meters. So this one is where you really have to pay attention to. So average velocity could be different than average speed once the object or swimmer turns around. So here I would just apply the average velocity function, which is displacement over time. The displacement would be simply 0 because the swimmer started from the left side of the screen, swam 50 meters to the right side of the screen, but hit the wall and turn all the way back and goes all the way back to where he or she started. So because you started on the left side of the screen and then you swam back to your starting point, so really you came back to the same position. So you really haven't changed any position. So your displacement in this case would just be 0. So anytime you make a round trip back to the original location, your displacement is always going to be 0 because there hasn't been any change in position. Okay, so position is different than distance, and usually that's where the confusion comes in. So average velocity requires change in position, but if you start and stop at the same place, there hasn't been a change, so the change is going to be 0. So in my numerator here, I have 0 meter divided by 48 seconds, 0 divided by 48 is just simply 0. Because the answer is 0 meters per second, you do not need to include any sort of direction, okay? Because the motion is 0, or the average here in this case is 0. So it's like the only time you don't need to include direction if the outcome is 0. All right, so in that, learn to differentiate between average speed and average distance. All right, I hope that helps. Don't be whack, stay nerdy.